problem 5D. So we're making another new function here. H of x is now f of x plus 4. I'm going to go to the original f of x function, which was x cubed minus 4x. I'm going to replace all of the x's with x plus 4. Once again, I'm not going to simplify. Let's go to the calculator and see what that does to the graph. Okay, so y equals, I think I can just come down here and change these minus 2's to a plus 4. Okay, that gives me what I want. And let's take a look at the graph. Of course, it's going to be some kind of shift again. This time the blue graph has clearly moved to the left. How many spaces? Well, here was an x-intercept at 2. Now it's over at -2. That's 4 spaces to the left. Or the one that was here on the blue graph at -2 is now down here at -6. So again, 4 spaces to the left. We'll say it shifted horizontally 4 spaces left. One of the things to notice here is that the signs SIG and S may work differently than what you expected. When I had an x minus 2 in there, the graph actually moved to the right. When I had an x plus 4, the graph moved to the left. So the horizontal changes are a little bit different than the vertical changes. Number 6, let's put this all together now. What have we learned? Once again, I have this function p of x. We want to write each new function in terms of p of x. Letter A, r of x is formed by horizontally shifting p of x 7 units to the left. Now, to make a horizontal shift, you have to change the inside of the function, the x itself. And we learned that moving to the left actually requires a positive. So it'll be x plus 7, p of x plus 7. Letter B, s of x, we're going to do 2 things to it. We're going to shift it 6 units down, and we're going to shift it 4 units to the right. Well, the right part, that's the new part here. That's the inside change. That happens to the x. To go to the right, I need a minus, so it'll be x minus 4 in there. 6 units down, that's the earlier part. That's the outside addition or subtraction, and we learned that down requires a minus 6 on the outside. Letter C, t of x, we're going to reflect p of x across the x-axis. That would be a vertical reflection, and then shift it 2 units to the left. Well, we learned about reflecting earlier. That was the one where you simply put a minus sign out in front of the function. So that'll take care of the vertical reflection. 2 units to the left, that's going to be an inside change here, changing the x itself. And again, left requires the plus. So I'll put x plus 2. The negative of p of x plus 2 would accomplish it. Problem number 7 gives some factoring practice. The directions say factor out the lead coefficient. Lead coefficient means the number at the very front. So the first one is very easy. The lead coefficient of 2, I can see it's a common factor to both of those numbers. And so I'll just undo the distributive property. Of course, I can check it very easily by distributing in my head. 2 times x would be 2x, 2 times 4 would be 8. So I'm done. Letter B looks a little tricky. The lead coefficient is 2, but there is no GCF. 2 doesn't go into 9. And yet, I can still do this if I wanted to. Factoring, after all, is really just dividing. Let's think about how that would work. I'm really just trying to put here whatever I would need to multiply by the 2 to get me back to what I had. Well, that would be x. 2x divided by 2 is x. How about the 9? Well, all you got to do is divide 9 by 2. We're supposed to work with fractions, not decimals. And that's it. That's going to be the number that you would have to multiply by 2 in order to get back to what you had, right? I can check that on the side. If I multiply 2 times 9 halves, I just get back to 9. Well, I can work letter C the same way. If I want to factor out that 2, simply divide each of those pieces by 2. 2x divided by 2 is x. Pi divided by 2 is pi over 2. And then for letter D, again, I can do the same thing. I'm factoring out that 2. So divide my pieces by 2. With pi over 3, it's probably easiest to think of it as multiplying by 1/2. That's the same thing as dividing by 2. That, of course, is going to become pi over 6. Again, you can check it by simply distributing. 2 times x, 2x. 2 times pi over 6, you can check that. You will get pi over 3. And so we're finished. Problem number 8, we just want to draw a couple of quick pictures. We only want one complete period, and we do want to show all the scale. Our first graph is the regular sine function. That's the hill and the valley. The period is 4, so I'll mark that on there. In fact, I'll put on my tick marks and count up to 4. The amplitude is 3, so as long as I mark 3 and then negative 3 down here, I think we'll be covered. The regular sine function starts at the middle, and then it goes to the high, the middle, the low, and back to the middle. And so here is one period of this function. Regular sine function, all the scale is showing. And then the second one, I want the reflected cosine function. That's the ghost. The period is pi, so when I mark out my 4 tick marks, pi will be out here. That means, of course, this middle spot would be half as much, pi over 2. And the first spot would be half of that. Half of pi over 2 would be pi over 4. I'm counting by pi over 4s. 1 pi over 4, 2 pi over 4. This one would be 3 pi over 4. And then 4 pi over 4 would be pi. My amplitude is 4, so I'll mark that on top and bottom. And then reflected cosine as the ghost starts at the low, then middle, then high, back to middle, and then low. Make sure it has that good curved shape. And I'm all set. It's reflected cosine, amplitude 4, period, pi.